Yeah, that should be
You will give
working.
like 2 minutes, Sebastian. Is that okay with you?
Yes, it's I just started recording. So I can edit it later because sometimes I forget and then I like halfway of the
It's fine.
presentation I remember.
Let's give another 3 minutes. Is it okay with you?
Yes, no problem. No, don't have anything to do today. Just so everything is set up and working. Okay, Laura told me that it was she was listening perfectly, so it's probably my connection.
Yeah. So the background of most of the people here is mainly audio DSP.
I actually don't know. I mean, we have Alex Brachler from Stuttgart. Giacomo Longo, that's my PhD student. Hena is from, she's in Bologna now. And then I have some names I don't, the Italians probably are from our course.
Okay.
But if you want in the chat to say where you are from, like what's your background, maybe.
I will do that on the presentation quickly.
No, I mean the people listening, if they want
Just
to.
1 second. Oh, yeah, okay.
Yeah. Do you prefer questions during the talk or at the end, everything?
Definitely. No. Please interrupt me. Unmute your mic and just throw the question. I'll be more than happy to take questions during the talk. That's more beneficial rather than leaving everything in the end.
Okay, great.
Be hesitant. Just unmute your mic and
Or
shoot.
put it in the chat if you are shy. Don't.
Yes, put it on the chat. You will be able to see it.
Yes, I will be looking at
Might
the
be
chat.
able not to see because I will be on full screen PowerPoint full screen mode. So
you will. I interrupt you if there is any question. Okay.
sure.
14:35, 5 minutes of waiting. I think that's enough. It's a pleasure for me to introduce, try to say it correctly, Spyros.
Yes.
Spyros Polychronopoulos. I love these Greek names.
Has like it's three names in one. Poly is many.
Many,
Chrono,
Chronos is time.
and Poulos is the child. So it's the child of the many times.
Okay, nice. And as well, I was saying, like he's one of the not failed musicians who's doing musical acoustics, and I think the work of Spyros it's really interesting because somehow going to the past to the ancient Greek instruments, but telling us how to do instruments in the future. We see it is optimization using finite element methods, DSP, and some weird Pareto sets, I think you call them. Yeah. And I'm really looking forward to hearing your talk and starting collaborating like next Monday or so. So, okay, the floor is yours. You can start. We are recording. Perfect. And
Thank you. Thank you, Sebastian, and thanks everybody else for being here in this talk. Thank you for the invitation. We are in an open channel with communication with Sebastian roughly a week now, or a couple of weeks, and I'm happy to be here. So I'm going to share my PowerPoint presentation with you guys. Let me. So Sebastian, I cannot see the chat. So if there is a question, just unmute your mic, or anybody else who wants to interrupt me and just throw a question, please feel comfortable doing it because it's the nicest way to communicate with people. Just unmute your mic and throw the question. So this is me, Spyros Polychronopoulos. I'm an acoustician and music composer. I'm a research fellow now and adjacent lecturer in the University of Athens. So a few things about me. I'm involved with sound since the early age, from this scientific aspect and its artistic aspect. And I have done a PhD in acoustics. I'm doing research, lecturing, supervised essays, and so forth. And artistic aspects, I'm doing album releases, and I'm basically composing music and playing my music and creating interactive sound installations and so forth. So I will be talking mainly about two of my works now in this talk. About my latest work, I got Sebastian's attention and we started talking, was the optimization method on the tuning, sound quality and ergonomics of ancient guitar using DSP and FEM simulation. And another work, an older work, like a couple of years ago, which is a acoustic levitation with optimized reflective metamaterials. And I will be talking about some other DSP projects that I have done, because Sebastian told me that you are more involved with audio DSP and you might find some other works a little bit interesting. So let's crack on. So during my PhD and a little bit afterwards, I was working with Helmholtz resonators. What is a Helmholtz resonator? Helmholtz resonator is basically a bottle. Imagine a bottle of beer that you blow and you hear a tone. That's a Helmholtz resonator, basically this bottle, and its resonant frequency is defined from its geometrical features. That would be the neck of the leg of the bottle, the opening, and the cavity. And you get a resonance frequency here in the frequency domain. So what we have done, we got Honorio Belli drawing from an ancient theater in Crete. That's a Greek island that was never actually found. This theater was never found. And Honorio Belli mentions in his book that he has found vessels underneath the seats of the audience. So they're depicted here in this drawing, the vessels, and we actually did a 3D representation of the theater, and then this is the drawing, a detail from the drawing, which is basically, as we see, a cavity and a resonator inside the cavity. And then we simulated the positions of the hearing positions and the resonator positions, and we got some results. Basically, the results were the center time and left was quite significantly changed using the resonators, and so maybe the cavities and the resonators in the cavity was used as a form of artificial reverberation close to because it works in the near field, it works close to the cavity and the resonator, you get an artificial reverberation. But that was about it. The rest of the indexes were not affected, so they were not mainly used after that, because we don't get much of an effect in other indices besides center time and left, as we found in open theaters, as this one. Another work was that DSP people might find interesting, that we simulated the Helmholtz resonator as a DSP model. Imagine you have a Helmholtz resonator attached and in a surface. So you have a bottle attached on a surface. And where do you get to see that? Basically, imagine you have a perforated panel. You have a perforated ceiling, as we have in some rooms, that you see perforations that could be treated as and seen as a lumped element, basically multiple Helmholtz resonators on our ceiling. So the first signal that reaches the receiver from source is the direct signal, and it was simulated with a delay pattern, and again, because of the time and the attenuation that you have in air. Then the second signal is the Helmholtz resonator signal, which is basically a delay from source to Helmholtz resonator and again. The Helmholtz resonator filter, and then a delay again, and then the reflection on the surface. You have a reflection on the surface, then therefore you have source, surface, gain, delay, panel, filter, and then again delay, and then we convolute both of these signals, which is the Helmholtz resonator signal with the surface, to get just one signal coming from the Helmholtz resonator surface, and we then sum up to get the output with a summation. If you have any questions, please interrupt. Why did we use convolution here and why did we use summation here? Please interrupt whenever you feel like interrupting. The reason is, like, if we added more and more Helmholtz resonators and we just did the summation, we get more and more acoustic pressure in the receiver, which is basically not physically right. You cannot gain energy out of thin air, obviously. And the convolution gave us the solution in this issue. I'm going to say a few things, but if you have questions, please don't hesitate. Then we added more Helmholtz resonators that you see now here, 4x4 panel of Helmholtz resonators. This is what you get. So source, receiver, the blue line, then the green line from Helmholtz resonators, the signals. It's omnidirectional, so the signal from Helmholtz resonators will always reach the receiver. So, and then one signal from the reflection of the panel. This is the DSP block diagram, which is basically the direct path of an impulse. Delta impulse, then the direct path, the panel reflection path, the Helmholtz resonator path. Summation, and then convolution, and then output. And this is what we got. This is in 3 octave bands, and we see the direct signal, and then this wimble from the Helmholtz resonators. So what we get to see now here is that we have an attenuation in the frequency that we expected to have the attenuation, right? In this frequency response. And then we actually correlated our results with a measured panel. This is the absorption coefficient. This is from 0 to 100%, and this is in the frequency domain. So let's, if there's not any other questions, let's go to the main work that I want to talk about. Is basically the physical modeling of, forget about ancient, but we did it for ancient musical instruments, but you can do it for any instrument. We find ancient instruments rather interesting because if you have, for example, a missing part of an instrument and you get to have like 2 bits of a wind instrument, for example, and you have found 2 bits of the instrument, and then with close collaboration with archaeomusicologists, you get to see, okay, this instrument needs to play these notes. Okay, so we get to predict the missing parts, geometry, and that we find a little bit interesting to work towards this direction. But for wind instruments, this is basically what was found. We find these kind of ruined instruments, not intact, obviously. This is an aulos, a wind instrument that used to play in 2 pieces. This is one of the 2 pieces. And this is the replica we built in our lab, which is basically these 2 pieces built, and this is the mouthpiece as well. Mouthpieces were never found. because it's from a tree that it cannot survive time. And we did the 3D representation of the instrument. And obviously you have, for example, if you are in the museum, you have pros and cons using replicas or using the real instrument in the museum. And the digital instrument has its own benefits. For example, in an exhibition center, you want to exhibit what you have found and so forth. This is what I was talking about. For example, if you have like a missing part and you have A and B, and you get to predict the missing part. And this is really interesting. Physical modeling is the only way forward because spectral unsampling is not going to work because you don't have the instrument intact and you want to predict. So you have to change the geometry constantly. Therefore, physical modeling is the only way forward. And what we have done in museums, we have built applications, as you see here. For wind instruments, the user gets to select the instrument, and this is wind instruments, this is string instruments, and you get to play with the instrument. You press run, and then you get to play the notes. You change the geometry as you want to change the geometry, and then you play with the instrument. This comes a little bit handy to have a little bit of audible interaction and maybe tactile as well with an application like this one, but not proper tactile. You don't get to actually play the instrument, but you play with a simulation of the instrument, and that's sort of a little bit engaging for people. And so the audience, the people who actually go to a museum, the number of the people is getting lower as the years pass by, but the money that museums spend for more interactive ways to actually attract people are getting more and more. Anyway, now we have built also Android and iOS games for, this is in Greek, I'm sorry, but we will do it in English as well. This is for kids up to 7 years old. This is 7 to 11, something like that. And this is for a little bit older kids. And this is the museum and the kiosk that we have introduced in the museums. So wind instruments, we have actually done the physical instrument, which is simulated as the mouth pressure, then the bore, parts. We have simulated the ancient instrument that was called Aulos, which was never been simulated as one instrument before. And then we compared the results with our proposed DSP model with the recordings. We built a replica and then we did the recordings. We used the same geometry and then we compared the results. And this is the simulation results, basically the audio files. You will not be able to hear the audio files most probably properly because they are being played from my speakers and then they go through the mic back to you. So you could, Sebastian, do you get to hear something or?
Yeah, you could hear something. You also can share your sound. If you stop sharing and share again.
Oh, it's fine. It's just 1 second clip. It's not
Yeah,
something
hear
really
something.
interesting. Okay, then for string instruments, what we have done something completely different because the geometry was a little bit more complicated, obviously, because you have the body of the instrument, which is a little bit difficult to simulate using DSP, just DSP. So we used digital signal processing just for the string vibration. And then if you convolute the body's impulse response calculated using finite elements method, you see here the model as the bridge basically transmits the vibration to the rest of the body of the instrument for the ancient guitar, also known as formings. Excuse me. Then you get the sound of the instrument. So this is the replica, taking into account what we have found in drawings, in documents, ancient documents, and so forth. We built the replica in our lab. Then this is the 3D model of this replica. Then we introduced it to finite element method simulation program that would be console, and then this is the mesh of the program, and then this is the analysis. When I say analysis, basically this is the impulse after 0.022 seconds. Then basically what we have done is we used cumulative synthesis, which is the impulse response of the body of the instrument was introduced to as an input signal for, instead of using just an impulse response, a delta function, we used the impulse response of the body as an input signal to excite the string DSP model, and then we got the output would be the sound of the instrument. Instead of just convoluting, we used cumulative synthesis. And what is cumulative synthesis is basically, it's very simple technique used many years now. It's basically the body, you have the impulse response, and then you use that impulse as an input for exciting the string. Then we had the physical instrument, which we actually built in our lab. We recorded the physical instrument, and then we compared the results. This is the results, for example, for one note in frequency domain. We have quite good results, good agreement. Then the idea moving forward, since we have a model that we can actually change the geometrical parameters, the body's material, and so forth, let's go and let the user decide what's interesting. That would be, we parameterize it as what's interesting for the user. Basically, we have three categories, main categories, that would be, as you see here, the weighting factors. That would be the tuning, the sound quality, and ergonomics of the instrument. For the tuning, we use just the central frequency for a tone to be played properly. The sound quality would be the main frequency and the overtones, and the ergonomics would be, let's play this instrument easier. And what's easier? We compare that with what's ergonomically good nowadays for an instrument. And the user gets to decide what's important. Then you turn a little bit up the tuning, you turn a little bit lower the sound quality, and so forth. And then the algorithm then computes. You get to play a little bit here as well with the lower and upper bound for the length of the string, because the string cannot be like 15 meters, for example. It needs to be in a certain bandwidth. So you get to decide and put the lower and upper bound for all these parameters, and then you get to choose the body's material. So for body's material, in order for the model to run fast, we just used 9 different pre-calculated body's material, that would be 9 pre-calculated impulse responses of the body. Why we did that? Because finite elements method was, why didn't we put FEM as well in the loop? Because it was slow. Now we are talking with Sebastian to overcome this difficulty, but would be really interesting to be able to actually change the geometry and the material of the body. That would be even more interesting to actually be able to interact with the instrument itself, as the body of the instrument, I mean. This is basically now the optimizer running, calculating what the user has defined as interesting, which will be these weighting factors plus the lower and upper bounds. And then you have case A, for example, case B and case C and case D, 3 different weighting factors for the same instrument. That would be W1 is 100% interesting, the rest is 0% interesting. That would be tuning is the only interesting thing, and I don't care about sound quality and ergonomics. And this goes for the other 3 cases, and the model gets to predict and optimize an instrument and actually propose building details, geometrical features for the instrument. As a future work, it would be interesting. It would be really interesting, as I said, to actually overcome this difficulty of finite element method, maybe using machine learning algorithms. We are in discussion of that. But another interesting thing would be the user to decide the instrument, the class of the instrument, as we say. For example, here I have selected wind instrument, then playing with the weighting factors, what's significant for me, then the obviously setting the variables, the lower and upper bound of the variables, and then the optimizer gets to run, then proposes a set of optimal variables, and then you have a 3D geometry of the instrument, and then you build the instrument. Maybe if it's a simple geometry like this one, for example, maybe you actually 3D print the instrument, and then you do what's really important, a UX test. You get musicians to actually play with the instrument and rate the instrument if the weighting factors agree with what they believe. For example, do you see my screen? Do you see me? Yes. I will stop the presentation now, the PowerPoint. Do you see me now? Yes, better? Yes, okay, cool. For example, if you have this, this flute, you get to introduce it to the optimizer, then you get to play a little bit with parameters, the weighting factors, the upper and lower body, the lower bounds of the parameters that will vary, and then you get to 3D print random geometrical features of the same instrument. So this one was proposed from the what I have done for the weighting factors, and this is another that I care about. For example, the tone, and this is I care about the ergonomics of the instrument, and then musicians get to play with these instruments, and then you get results, UX results, real results from real users. That would be a step forward, going forward towards actually optimizing and machine learning, and the machine gets to propose of instruments that would be interesting for humans. Do you have any questions so far? Is it, do you understand everything?
I like to go into more detail into the sound quality definition, because your definition in the paper is quite particular for this instrument, and I don't know how like
Generalization, you mean?
Yes, yes.
How
And
can you actually generalize when it comes to sound quality? Sound quality is in this paper is it was really not described as I wanted to describe it, because it has to go a little bit more in depth. I agree with you. And you need to take into account psychoacoustics. If you go towards this path, that would probably, not probably, definitely, you will have a generalization of what's audibly expected. I don't want to say pleasing audibly, but expected. When you play an instrument, you expect the fundamental frequency and then doubling the frequency to be like the first overtone, the second overtone, and so forth. If you don't get that and you have like a little bit of deviation there, or if you have, for example, I play Do and Do an octave higher, and I don't have the double frequency from the fundamental of this Do to the next one, you get a weird sound. So you expect the overtones to overlap, and as you play, you expect the overtones of an instrument to overlap and the fundamentals actually to be double if you play one octave higher. This is what I call sound quality of an instrument, but you need to take into account, to make it more a broader definition of sound quality, you need to work really hard on psychoacoustics there, and trying to have a general, more general approach. Okay. So let's move. Helena.
Can I ask about the string model, the DSP model?
Sure.
Can you explain it in a bit more detail? I mean, and I'm also curious about for this agent guitar, like, because you saw the spectrum between the measured and the simulated one, but I would be interested in hearing, like, either hearing the samples or hearing your description of how are they still different. Like, does it capture the physics of the instrument well enough, the DSB part, or do you think the string model should be more maybe mathematical, let's say, or more contain more non-linearities and things like that? I mean, depends. I don't know how exactly the string model is.
Yes.
So, yeah.
Interesting question, Helena. Thank you. So the next slide would be me playing samples from these ancient instruments that were simulated with this method. So basically, the idea of simulating instruments in that way it's not very new. You actually use impulse response from the body and then maybe convoluted, or use this cumulative synthesis that I described here, and you have the result. And then you change the string model, you have the body, and then you change the string as the tension and so forth, and you get different notes from the instrument, from the same instrument. I believe that if you want to go in more details, that will be describing the FEM simulation in more details. The string DSP model, I think it works perfectly fine for more than 40 years now. We have the string as a DSP model, but the body needs to be a little bit more. It's a little bit more involved because the geometry is not very easy. You have cavities, you have instrument makers have this underneath inside the guitar, for example, they put like pieces of wood that would tune the body of the instrument, and all these were neglected obviously in our FEM model. All these small tricks play significant role, and would be really interesting to actually have all these things that actual musical makers use to build an instrument, to have that as in your simulation, as the simulation of the body of the instrument, which is the most interesting bit of the simulation of string instrument.
Can I also actually, yeah, thanks for the answer. I would just like to ask one more thing. Like, so this DSP, this model is modeling the string vibrations in 1 dimension, right?
Yes, this is 1D.
Yeah, so I'm thinking like for this, well, I don't know this ancient guitar very well. Do you think there are also other, like how important would the
I see
other
what you
vertical
mean.
vibration be, or like the longitudinal vibrations? I don't know the sound of the instrument, so.
Might be okay. That's a good point, Elena. That's a very good point. But I believe that basically you get all the vibrations on the bridge of the instrument. So the interesting bit would be to see actually if the musician is not planking the string just up, but you have a little bit friction in other directions as well. That would be interesting also to see that, but the coupling would be a little bit more yes, because now you use, that would be a little bit more involved, and it would be interesting to see this effect of the instrument, but you need to not use the string as a DSP model. That would be basically taking the string in finite element method domain as well, and having a model just in FEM, and then playing with the string in 2 or maybe even no, in 2 dimensions. All good. Moving forward. I think we're moving forward. We heard okay, and now few things about acoustic levitation. I don't know if you find this interesting, but it's less DSP oriented. So what we do for acoustic levitation is basically we levitate an object right above a PAT, as we say, a phased array of transducers. So you see the object here levitating. These transducers are transducers emitting high frequency ultrasound in very high level. That would be 155, close to 155 decibels. And what we actually do in physics point of view, you create a cavity, as you see here, a cavity of low pressure point, then around it maximum pressure point, so you trap the object, and then you move the object around. How do you do that? Basically, what we do is creating delay patterns. We delay the signal from this transducer, and we delay with a different delay the signal from this transducer, and we shape the field likewise accordingly to have a levitation point here, for example. I will explain a little bit more here. As you see, this is a standing wave. So you have this and this bit. This one is moving with maximum acceleration, and this one is not moving at all. For example, you have like in standing wave, you have nodes and antinodes. That's acoustics 101 now, but this is where the object levitates. So you have a transducer and maybe a reflector on top, or you have a transducer and a transducer on top, it's the same, and you have this standing wave and this beat, the small sample levitates in the antinode. As you see here. So this is the transducer, one transducer, you get to see the standing wave. This is called the Schlieren mirror. You have this Schlieren mirror with a fog here, and you see the standing waves. The fog goes where the antinodes are, and the object levitates in one antinode. You have high pressure underneath, high pressure on top, and you have zero pressure when where the object levitates. So this is basically what's, excuse me, something happened with PowerPoint. I don't know. Something happened. Hold on 1 second, please. Okay, what we have done, basically the main idea was to have levitation points in more than one position, to have multiple levitation points, basically. So what we have is a field. Imagine this cavity between the transducers and the reflector. We have this cavity that we want to control. So we have the direct signal from the transducers to a point in the cavity, a certain position in the cavity, and then you have the reflecting signal from the reflector. So this is the pressure that you get anywhere in the field, in this cavity. So what we have done, the idea was to actually delay not the direct signal as the transducers, you get to introduce delays. We got to delay the reflectors signals. So we built a grid of reflectors here, as you see, with different heights. So you imagine you have a datum, and then you have one element of the reflector a little bit lower, another one a little bit higher, and so forth, to create this delay pattern that will shape the field accordingly. So our first attempts, this is basically a simulation using calculations. This is basically our calculations of the field. This is the FEM elements method simulation of the field. Very good agreement. We were really happy. And then we put the transducers, and then we actually measured. We measured with a microphone in the field, and we measured the field, and it was like this. Very bad results. And the reason that we had bad results, we thought it was basically because we had made two assumptions. The first assumption was that we have a plane wave propagation. According to the literature, if you have a board with transducers, even ultrasound transducers, and you turn it on and they all have the same phase, you have a plane wave propagation from the board upwards. And this is not what's happening here, basically. This was the propagation assumption, that it's a plane wave, and the second order reflections were neglected. So you have transducers, reflector, and then the signal reflects back to the transducer and it reflects back to the field and so forth. So second order and above second order, obviously, reflections were neglected, were thought to be non-significant. So first things first, the investigation of plane wave propagation. We tried various ways to actually achieve a plane wave propagation, taking into account what the theory says, that a source needs to be a lot smaller than the wavelength in order to be properly omnidirectional source. These were some simulations. I don't want to bother you with all these details, but what we have actually done, we have 3D printed and laser cutted various materials that would go on top of the transducers to actually achieve a plane wave propagation. And we tried various methods and we didn't succeed. So basically what we have done afterwards, we kind of forgot this scenario. We went back to our equations and the equations became a little bit more involved, a lot more involved, that we had all of these signals. We had 16 by 16 transducers, 16 by 16 reflections, and the equations, the mathematical equations were a little bit nightmare, but we had to do it. Now second order reflections were neglected. We ran some simulations using COMSOL, and then we did the measurements as well. We were right that the second order reflections were non-significant. Third order, so it's fine. So then we used multiple sources, and this is the FEM model. This is our equations, which is really close, and this is the difference. And we were really, really happy to see that the model was working afterwards, but it was a little bit pain to actually calculate all these signals. Imagine you have one signal from this transducer to a point, then going back here and then reflecting back, and this is for all the transducers and all the reflectors, all the elements. Now we introduced an objective function that would be basically an objective function described as such, which is basically a number of levitation points. That's the levitation condition. Don't worry about this equation too much. And this is all levitation points have good equal quality. We enforce the optimizer to actually output same quality levitation conditions for all the positions that we introduce. And this is the optimizer running for two positions, two levitation positions. You see here objective 1, which is the objective for levitation point 1, objective 2 for levitation point 2, and this is the standard deviation between these points, which is actually what you want to have good levitation points, good two levitation points. And you see here the position of the position of the reflecting elements changing. And the field obviously changing. And this is the main objective function. Okay. And then we 3D print the proposed arrangement of, so this is what we call the metamaterial, the displacements, and we have levitation points here and here, here and there, and this is a smiley face. And this is basically the metamaterial, as you see here, if you see my screen. This is the metamaterial in transparent, and this is the metamaterial non-transparent. And moving forward, that would be interesting to actually have a reconfigurable metamaterial to be able to control the reflectors, the elements of the reflectors. that would be all for me.
Thanks a lot.
Thank you, Carlo.
How do I clap?
Thank you guys.
Yeah, super interesting. Anybody has more questions? You, Stefano. Or, yeah. First Stefano, then Michele. Okay, Stefano? Not, no. Michele, if you want to go, you can unmute yourself and just make a question. Michele Murciano? No, you have your hand raised.
Maybe by mistake, maybe both by mistake.
Okay. Hiena, you have more questions? I'm gonna start calling names.
It's fine. If there are no more questions, or if people feel
I
like
I have a question actually. Like, what's the sorry to cut you off like that. What's the future work that you're going to do with the musical instruments? Like, I mean, you mentioned that you will maybe try some machine learning stuff.
we are discussing now with Sebastian few things to actually overcome this bottleneck, which is the issue that we have with finite element method, that they are actually really slow, and that didn't allow us to introduce the whole model in a loop, basically, in the optimizer. We want to do that. We want to introduce that in the optimizer, so the model is really beneficial now, because what this paper is introducing something which is, there you go guys, we can actually work towards this direction, optimizing instruments that way. But to be honest with you, it's not 100% parameterizable. As you saw, basically the main parameterization is on the strings, which is basically not a very an ideal parameterization. The really interesting, and the parameterization of the body is basically 9 different materials. That's about it. It would be interesting to be for the music maker to actually parameterize the instrument as the music builder actually parameterizes the instrument. That would be parameterizing the body, the shape, and having weird shapes for an instrument, and the machine being able to propose a very weird shape for an instrument that we have not even thought about.
Actually, what is the string material in those agent are the formings and
It's from guts.
that's okay. Yeah.
Is animals' guts.
No, it's very interesting work because I'm now working in Bologna in a project where we try to do numerical restoration of harpsichords and other cedar instruments.
Okay.
But we have taken the approach of FTDD actually. I mean, it's from the professor that
FTDD and okay.
yeah. So I'm working towards that stuff. Also to use FTDD for the strings, so we get more flexibility with the string modeling as well. As opposed
More
to
flexibility, definitely would be interesting. Yeah, your question about longitudinal waves and the string moving into two axes would be interesting to actually see what's going on there as well.
Yeah, because this seems to vary from string instrument to string instrument depending on how the string is attached to the body. Like in the instrument that I'm looking at, which is like an old Finnish zither, it's tuning pins on both sides, so there's no bridge. So there's much more flexibility in the boundary conditions. So this gets already quite complicated. There is, however, a DSP model from 10 years ago using the same methodology that you're using, but it's missing some of the key features of that make that instrument sound. So this is why I was asking you, like, how does the instrument actually sound, and how well does this DSP capture that?
How we believe that this is actually the problem with instruments. It's so chaotic the way it's very chaotic. We found it a little bit easier. That's why we used string instruments. In winged instruments, it's even more chaotic. That with the same fingering, a musician gets to play with playing with the mouth a little bit more open, a little bit more closed, whatever. Gets to play like 2 octaves even. In some instruments that, for example, aulos has double reed. With double reed, you get to like bite a little bit the reed, you get to open a little bit, and you get to play even 3 octaves with the same fingering. I saw that and it was like mind blowing, 3 octaves almost. So whatever we say, we study the instrument. If you don't study the musician interaction with the instrument as well, I published another paper. It's called Endro Tuner, which is basically tuning the musician interaction with the instrument. That's really important. And if you don't study that as well, you don't have an instrument without a musician playing the instrument. So, and if you take into account the musician, which is actually a human being, that's a little bit way too chaotic. I don't know. But there is something there. Since there are really good instruments and really bad instruments, there are good and bad musicians as well. But since we call an instrument good, and there is a criterion, and I'm an instrument builder, and I'm a very bad one, and there is another one which is a really good one. Something is happening there. We need to study what's happening there. There is some truth. As we say, good and bad music. And we keep discussing about good and bad music, and there is no such thing as good and bad music, but we keep discussing this.
Yeah.
So,
Carlo Beccherucci asked, what could be an application for acoustic levitation?
there are multiple applications for acoustic levitation as we speak, Carlo. For example, there are like in chemistry labs, they levitate 2 droplets. Magnets are really more powerful. The magnets levitate trains, but they cannot levitate liquid, for example, if it's not magnetic. So imagine you have like a chemistry lab, you levitate 2 droplets and you mix them in thin air, and you don't get to touch the liquid, you don't contaminate the liquid. Then you have other things happening in space shuttles, and you want to place sugar there and another bottle there, and the only way to do it is basically using acoustic levitation, and you get to place objects around and move them around when there is no gravity. Another application would be like to have a 3D display, creating 3D shapes in midair with objects. A colleague of mine published a paper like 2020, Nature, and it was about 3D display using levitation. And then another scenario as well, which be a very optimistic one, is to be able to levitate very, very, very small objects. That would be a cell, for example. Imagine you have a cell here, that you have a cancer cell, and then you track the object, you grab it, and you remove it from the tissue. And so forth.
Cool.
Plus, acoustic levitation is very, very sexy.
And if you add metamaterials, it sounds even better.
Everything is meta now, Sebastian. Everything is
Yeah.
meta. We live in meta age, so everything is meta.
Meta times. Okay, I think we sank again. Spyros, it's been a pleasure. I'm going to stop recording.